Hello everyone. In this video, we'll build a decentralized exchange market maker that simulates liquidity provision in price bands, similar to how Uniswap V3 works. This implementation will demonstrate how liquidity providers can add liquidity to specific price ranges, earn fees from trades, and how the liquidity distribution changes as the price moves. To start with, let's look at the necessary headers. We include IO stream for input and output streams, string for string operations, map for ordered data structures, vector for storing collections of liquidity positions and trades, IO manip for formatting output with fixed decimal notation, CMath for mathematical operations, and algorithm for standard algorithms like remove if. First, we define our liquidity position struct. This represents a single liquidity position provided by a market maker in a specific price range. The struct has 6 fields: ID as an integer to uniquely identify each position, price lower as a double representing the lower bound of the price range, price upper as a double representing the upper bound of the price range, amount token 0 as a double representing the amount of token 0, which could be a stable coin like USDC, amount token 1 as a double representing the amount of token 1, which could be an asset like BTC, and fees earned as a double tracking how much in fees this position has accumulated. The constructor takes 5 parameters: I for ID, lower for price lower, upper for price upper, token 0 for amount token 0, and token 1 for amount token 1. In the initializer list, we set fees earned to 0.0, meaning when a position is first created, it hasn't earned any fees yet. Next, we define a trade struct. This represents a single trade event that occurs in the pool. It has 4 fields: price as a double, representing the price at which the trade occurred; amount as a double, representing how many units of token 1 were traded; is a buy as a boolean, where true means buying token 1 and false means selling token 1; and fee paid as a double representing the fee amount paid for this trade. The constructor takes 4 parameters: P for price, AMT for amount, buy for is buy, and fee for fee paid, and uses an initializer list to set all the member variables. Now we define the DEX market maker class. This is the core of our market making system. The class has several private member variables. First, we have current price as a double, initialized to 50,000.0, representing the current price of the pool. We have positions as a vector of liquidity position objects, storing all the liquidity positions that have been added to the pool. We have fee rate as a double set to 0.003, which represents a 0.3% fee rate, similar to Uniswap V3's 0.3% pool. We have total fees earned as a double, initialized to 0.0, tracking the cumulative fees earned across all positions. We have trade history as a vector of trade objects, storing all trades that have occurred for analysis and tracking purposes. The class has several private helper methods. The isPriceInRange method takes a price as a double and a constant reference to a liquidity position, and returns a boolean. It checks if the given price falls within the position's price range by comparing price to pos.price lower and pos.price upper. This method is marked as const because it doesn't modify any member variables. The calculate liquidity distribution method takes a reference to a liquidity position and a price as a double. This method determines how the liquidity is distributed between token 0 and token 1 based on where the current price is relative to the position's price range. In Uniswap V3, liquidity distribution uses the constant product formula, but for simplicity, we use a linear distribution model. If the price is not in range, we check if the price is below the lower bound. If so, all liquidity is in token 1, which is BTC in our example. We set amount token 0 to 0 and convert all value to token 1 using the lower bound price. If the price is above the upper bound, All liquidity is in token 0, which is USDC. We set amount token 1 to 0 and convert all value to token 0 using the upper bound price. If the price is within the range, we calculate how far through the range the price is. We compute range size as the difference between price upper and price lower. We calculate price from lower as the difference between the current price and the lower bound. We then compute ratio as price from lower divided by range size, giving us a value between 0 and 1 representing where in the range we are. We calculate the total value of the position by adding amount token 0 and amount token 1 multiplied by the current price. We then distribute this value proportionally. Amount token 0 gets total value multiplied by 1.0 minus ratio, meaning more token 0 when price is lower in the range. We calculate amount token 1 by subtracting amount token 0 from total value and dividing by the current price. The distribute fees method takes a fee amount as a double and a price as a double. This method distributes trading fees to all liquidity positions that are active at the given price. We iterate through all positions using a range-based for loop with auto and ampersand to get a reference. For each position, we check if the price is in range using isPriceInRange. If the position is active, we calculate its share of liquidity by adding amount token 0 and amount token 1 multiplied by the price. We then calculate the total active liquidity by iterating through all positions again and summing up the liquidity of those that are in range. This gives us the total liquidity available at this price level. If total active liquidity is greater than 0, we calculate each position's share as its liquidity divided by total active liquidity. We then add fee amount multiplied by share to the position's fees earned and also add it to total fees earned. This ensures fees are distributed proportionally based on how much liquidity each position provides. Now let's look at the public methods. The add liquidity method takes 4 parameters: price lower and price upper as doubles, defining the price range, and amount token 0 and amount token 1 as doubles representing the initial amounts of each token. We create a new position ID by taking the current size of the position's vector and adding 1. We create a new liquidity position using the constructor with these parameters. We then call calculate liquidity distribution to determine how the liquidity should be distributed at the current price. This is important because the distribution depends on where the current price is relative to the range. We push the position to our positions vector. Finally, we print a message showing the position details using fixed and set precision with 2 to format prices to 2 decimal places. The remove liquidity method takes a position on which ID as an integer. We use remove if with a lambda function that checks if a position's ID matches the given position ed. The remove if algorithm moves matching elements to the end of the vector and returns an iterator to the new end. If we found a matching position, we erase from that iterator to the end of the vector, effectively removing the position. We print a message confirming the removal. The execute trade method takes an amount as a double and an isBy Boolean. This simulates a trade occurring in the pool, which updates the price and distributes fees. We calculate price impact as amount multiplied by 0.0001, representing a 0.01% impact per unit traded. This is a simplified model. In reality, Uniswap uses the constant product formula, which creates nonlinear price impact. If isBy is true, meaning someone is buying token 1, this pushes the price up. We calculate new price as current price multiplied by 1.0 plus price impact. If isBy is false, meaning someone is selling token 1, this pushes the price down. We calculate new price as current price multiplied by 1.0 minus price impact. We calculate the trade value as amount multiplied by current price. We calculate the fee as trade value multiplied by phi rate. We create a trade object with the current price before the trade, the amount, the is by flag, and the fee, and push it to trade history. We call distribute fees with the fee amount and the current price, which distributes the fee to all active liquidity positions. We then update current price to the new price. After the price update, we need to recalculate the liquidity distribution for all positions, since the distribution depends on the current price. We iterate through all positions using a range-based for loop and call calculate liquidity distribution for each one. Finally, we print the trade details using a ternary operator with is buy to print either buy or sell and format the price and fee to 2 decimal places. The update price method takes a new price as a double. This simulates an external price movement, perhaps from another exchange or market data feed. We update current price to the new price. We then recalculate the liquidity distribution for all positions, since their token 0 and token 1 amounts depend on where the current price is relative to their ranges. The print positions method is a const method that displays all liquidity positions. It prints a header, then sets the output format to fixed decimal notation with 2 decimal places. It prints the current pool price. If the positions vector is empty, it prints a message and returns early. Otherwise, it iterates through all positions using a range-based for loop with const auto and ampersand. For each position, it checks if the position is active by calling as price in range with the current price. It prints the position ID and whether it's active or inactive. It prints the price range, the amounts of token 0 and token 1, and the fees earned. If the position is active, it also calculates and prints the current value of the position by adding amount token 0 and amount token 1 multiplied by current price. The print summary method is a const method that displays summary statistics. It prints a header, sets the output format to fixed decimal notation with 2 decimal places, and displays the current price, total number of positions, total fees earned, and total number of trades from trade size history.size. It then counts how many positions are currently active by iterating through all positions and checking if each one's price range contains the current price. It prints the count of active positions. The class also has 3 simple getter methods: get current price, get position count, and get total fees, all marked as const, which return the respective member variable values. In the main function, we create a DEX market maker instance named We print a header message explaining that we're simulating liquidity provision in price bands. Similar to Uniswap V3, we then add several liquidity positions to demonstrate different strategies. We call print positions to display the initial state of all positions. We then simulate several trades. For the first trade, we call execute trade with 0.05 as the amount and true for is buy, representing a small buy order. We print the positions again to see how the price change affected the liquidity distribution. For the second trade, we call execute trade with 0.1 as the amount and false for is buy, representing a medium sell order. We print positions again. For the third trade, we call execute trade with 0.2 as the amount and true for is buy, representing a large buy order. We print positions again. We then simulate an external price movement by calling update price with 51,500, representing a market move to a higher price level. We print positions to see how this affects which positions are active and how liquidity is distributed. We execute one more trade at the new price level, calling execute trade with 0.15 as the amount and false for is buy, representing a sell order. We print positions again. Finally, we call print summary to display the final statistics, showing the current price, total positions, total fees earned, total trades, and active positions count. The program also prints key concepts explaining how liquidity provision in price bands works, including that only active positions earn fees, positions become active or inactive as price moves, and that narrower ranges provide higher capital efficiency but require more rebalancing. We return 0 to indicate successful program execution.